Hello, my name is Aki Ishida. Thank you for the introduction. Thank you in particular to Lee Ren of Perkins Eastman and the AIA-DC Asian American Designers Union for this invitation to give a talk. My work in both writing and design center around aspects of architecture that are temporal, impermanent, and ever-changing. This includes aging of buildings over the course of their lifespan and mutable readings of architecture, in particular glass architecture. In 2020, early in the pandemic, I published the book Blurred Transparencies in Contemporary Glass Architecture, Material Culture and Technology, which examines material of glass in broader cultural and social contexts. Today's talk focuses on one of the chapters. It is the Toledo Glass Pavilion by Sana, Sejima, and Nishizawa. And it happens to be the one of two chapters in the book that are on works of architecture by Asian architects, the other one being I.M. Pei. And I thought this choice would be appropriate for this series. Just to give you a little bit of background of my professional work with glass, I'll share some slides of the work that I did at the office of James Carpenter, who is an artist trained in with glass at the RISD, Rhode Island School of Design. I worked in his studio immediately following graduation from graduate program at Columbia. And this was the first project I worked on. I learned a tremendous amount about both phenomenal qualities of glass, meaning the effects that glass can produce with light, as well as technical aspects of architecture, how glass behaves under different pressures, how you structure, you work with glass in structural ways, and how you detail glass so that the effects of the material can be foregrounded. This is glass Grimwall at the Scottsdale Museum of Contemporary Art. It's an exterior enclosure for sculpture garden, and so you can see the effect on the image on the left. This uses dichroic glass blades, which transmits one color, and then it reflects the complementary color. But this is showing a close-up detail of the dichroic glass held between larger panels of diffuse glass. So in working with real materials and seeing my drawings come to fruition with real glass materials helped me to really understand material properties of glass as well as their optical effects. And glass takes on very different appearance depending on how it interacts with light and where the position of the light is and what time of the day it is. It's particularly dynamic in exterior conditions, but with electric light, you can manipulate the effects in a very varied ways. This one example uses cast glass. This was called a lens wall in a lobby in Times Square, New York City. And we worked with glass casting artist in Oakland, California to cast these custom-made lenses, which we suspended from these glass rods that were machine milled by tri-pyramid structures. The last example from Carpenter's office is this. It was the first glass cable net wall in the United States. We worked with German engineers who had extensive experience designing cable net structures in Europe, in particular Germany. And we worked with the building architect SOM to create this very transparent wall for, on the upper part, the Jazz at Lincoln Center performing art space, and on the lower part, the shopping mall and the retail spaces. And in both cases, maximum transparency was requested. And I often explain to my students that, think of this as a tennis racket, where you have these cables that are able to flex when the wind hits it, just like a tennis racket flexes when the ball hits the net. And at the intersections of these vertical and horizontal cables, there are these clips that are clamped onto the cable, and it also acts as a corner clamp for very large sheets of laminated glass. And this is a view from the interior. Following my professional practice, I practiced for a total of 17 years in New York City. I entered full-time academia, teaching as a tenure-track professor at Virginia Tech, where I still teach. And in my courses, I applied much of my knowledge that I gained in professional practice, particularly in respect to building materials, to introduce beginning students, second-year Bachelor of Architecture students, to these individual materials. I'll show some examples of hands-on exercises, which I try as much as possible in a lecture class to combine into more traditional lecture delivery format. So students are asked to work in teams and cast these concrete blocks, for example, when we talk about use of concrete, where raw materials for concrete come from, and what properties concrete has. They are asked to make modular blocks of concrete that can be stacked to transmit light. And students experiment with different formwork and different dyes, different modules that can be stacked in various ways to transmit light differently. I also asked them to take pieces of glass, which were donated by James Carpenter's office, and take photographs to study different optical effects of glass. So how does light reflect when it hits a glass surface? Or how can light be transmitted, or the effect of colors be expanded if you bring a diffused light close to a diffused glass close to a light source and colored papers. To teach about wood, I had them construct I think roughly 2x2 wood panels that also transmit light, but using only dry fit joints. So no nails, no screws, no glue, just wood. Having taught that class along with second and third year studios, I wanted to write a book that reflects on what I learned in professional practice, combined with how I saw my students learn about glass through material experiments, as well as through very close observation of glass. There are different types of books on glass, including technical manuals. These books by Burkhauser are, these are books that we often find students referencing when they draw building sections. There are, like the one by Fiden, this is a comprehensive survey of glass buildings, both historical and contemporary. There are also scholars who have written about glass structures or glass objects, focused on very particular periods in history. So this one is by Armstrong on Victorian glass. There are other historians and theorists who have focused on use of glass in particular countries during a very particular period. I made a proposal to Routledge to publish this book as a book written on glass through the perspective of a practitioner or designer. And it's a close examination of 6 glass buildings examined in the context of both technology and social cultures. A material that is neither liquid nor glass, or liquid nor solid. Glass is amorphous, hovering between the 2 states. In a near magical process, ordinary sand is transformed into a fragile, see-through material. This transformative nature of glass has captured people's imagination throughout history. From the 11th to 16th century, the secrets of glassmaking were highly coveted by the Venetians, until 3 glassmakers were smuggled by King Louis XIV for the Hall of Mirrors at Versailles. Glass's historical exclusivity continues to shape metaphors associated with glass today. Crystals, glass, and mirror have appeared symbolically in literature, art, and architecture, both religious and secular. Glass slippers, coffins, and mirrors are often metaphors in fairy tales, which describe the collective dreams of a culture. In modern architecture, glass is a material imbued with idealism, symbolism, and utopic vision. Glass's fragility, which intensifies its exquisiteness, along with difficulties in thermal control, have challenged architects over the past century. As Rosemary Hogg-Bletter writes, because of glass's preciousness in pre-industrial periods, coupled with its brittleness, glass appeared frequently in architectural fantasies, in the, quote, realm of wishful thinking, unquote. Glass is physically heavy, but metaphysically light. Together, this is the basis of the paradoxical nature and allure of glass. Glass, in a seemingly multivalent contradiction, combines immaterial qualities with material properties. Following an accelerated development in material and engineering of glass in the past few decades, the knowledge about both spatial effects and technical performance of glass have greatly expanded. In this time period, architecture has witnessed an emergence of technical advancements, including chemical coating that alter reflective and refractive properties, plastic lamination interlayers that give structural stiffness to glass panels, and fabrication techniques that allow precision machined hardware to become embedded in glass. Is an example of embedded glass or embedded hardware in glass. Consequently, the structures that could only be drawn or written about previously, including those by prophetic poet Paul Scheerbart, have now been realized. As material properties are altered, they in turn call into question the prevailing social and cultural symbolisms and metaphors associated with glass. Glass transparency must now be reconsidered in the context of recent developments and cultural changes. The prevailing perceptions of glass have become blurred, both materially and physically. Transparency is both fundamental and elusive. In architecture, its metaphorical meanings are as multivalent and mutable as the visual effects of glass, varying temporally and spatially. The medieval Latin root of the English word transparent is transparere, meaning shining through. The Renaissance architect Filaretti describes transparent materials like glass as diaphanous, a word with a Greek origin meaning to show through. The Japanese word for transparency is toumei. The character to means to permeate, and mei is brightness or clarity. This material quality gives glass a nearly magical significance that has been noted for centuries and led to the widespread theory that transparent objects capture and hold light within themselves as if beacons. In this way, glass enters the imagination as a materialization of light, a substantial spirituality. To blur means to make the difference between two things less clear. In optics, the blurring of an image is related to the depth of field. When the human eye looks at an object, the object in focus appears sharp on the retina, but objects in front or behind appear blurred. As the focal plane moves within the depth of field, so do the areas that are less focused. In other words, blurring is relational and mutable. In architecture, when glass is experienced in motion under changing light, the perception of it is not simply transparent, but is a specific kind of transparency that can be called blurred transparency. As new techniques in glass making have expanded the range of effects and performance of clear glass, its transparency is increasingly multivalent and complex, making nuanced differences difficult to perceive. As the perception of material becomes more blurred, the prevailing cultural and social meanings associated with glass are also blurred. What may be indiscernible to the eye can have a substantial impact on the overall appearance and performance of a glass building that in turn impacts one's experience and challenges prevailing meanings associated with the material. These properties can enable spatial effects and performance that were previously unobtainable and consequently not fully included in architectural discourse. Despite its ubiquitous presence in contemporary architecture, glass transparency seldom has been examined deeply. Colin Rowe and Robert Slutsky's 1963 classic essay, Transparency, Literal and Phenomenal, remains a tenet of architectural thought. Rowe and Slutsky consider the perceptual and compositional potential of transparency in paintings and architecture, but assume, rather than examine, its relation to materiality, specifically to glass. They define material transparency of glass as literal transparency, which they dismiss as unambiguous and limited in interpretation. Over time, the limitation of their binary understanding of transparency have been critically questioned. These include the light construction exhibit of 1995 at the MoMA and the 2007 Engineered Transparency Symposium at Columbia University. In order to deepen and broaden readings of glass transparency, the book Blurred Transparencies explores the interweaving of historical, theoretical, and cultural aspects of glass buildings, along with the practical. This book brings to light the complexities in transparency of glass through close observations of 6 pivotal works of architecture. All are built with optically clear glass, not diffused or textures, which are in some ways inherently blurred, for their exceptional effects, which allows the focus to be on the qualities of transparency and reflectivity in glass. Each building is selected to demonstrate how its glassy qualities transcend transparency as it has been understood in the discourse of modern architecture. And this is the chapter that I'm going to discuss in depth. The glass pavilion at the Toledo Glass Museum, designed by Kazuyo Sejima and Ryue Nishizawa of Sana, presents a novel kind of transparency that results from layering of clear glass and volumes of air. Built with clear glass as the primary exterior walls and interior partitions, the pavilion is simultaneously opaque and transparent in its construction and spatial organization. It is opaque in its concealment of steel structure, which makes the transparent ribbons of massive glass possible. At the same time, it is remarkably transparent in exposing the elements of architecture that are typically hidden from view, notably the plenum made of clear glass. These see-through plenums make radical programmatic adjacencies and visual connections. These novel transparencies at Toledo result from several mutually dependent factors. One is an innovative approach to mechanical and structural engineering, and the other are balance of light and reversal of structural and material hierarchies, and a spatial organization of glass-enclosed air plenums and rooms. The coupling of air and glass can be traced to human breath that, prior to industrialization, shaped molten glass into blown cylinders, which were then cut and flattened into sheets of glass. Exhalation of air from human lungs transformed fluid glass into frozen liquid. Isabel Armstrong, scholar in British literary and cultural studies, writes that glass bequeathed, quote, congealed residue of someone else's breath, annealed in the substance he worked, unquote. The glass pavilion's transparency is soft, watery, and intimately airy, in contrast to the hard, cold, and machine-made impression often associated with glass. The softness of the pavilion is further underscored by its play of layered reflections. The glass pavilion is a carefully calibrated instrument of light, shadow, and reflections. Although clear glass is the predominant material, the building differs from the see-through transparency of modernism described as shadowless glass blocks in Ludwig Hilbersheimer's 1929 essay, Glass Architecture. Hilbersheimer writes that Paxton's crystal glass, quote, obliterated the old opposition of light and shadow, which had formed the properties of past architecture. It made a space of evenly distributed brightness. It created a room of shadowless light, unquote. Likewise, the pavilion is distinguished from the diffused, shadowy luminosity of translucent glass buildings. In contrast, however, the use of curved, massive monolithic glass in the pavilion leads to an intensified transparency in which a clear material gives mutable readings ranging from apparent depth to near opacity. This layering of glass and air engenders a glass transparency of deep, dense, yet diaphanous space that differs from ordinary curtain wall skyscrapers or the canonical modern glass buildings such as the Farnsworth House. Reflections seen through multiple curved glass sheets belies the material's characterization as merely transparent. The original Toledo Museum of Art was founded in 1901 by the owners of Libby Owens Sheet Glass Company, maker of windshield for the automobile industry and sheet glass for building construction. The pavilion stands across the street from the main museum on a flat site among 150-year-old trees. So this is the original museum, and this is the glass pavilion. It is a freestanding one-story museum that exhibits a collection of over 7,000 glass objects. The name pavilion was chosen by the museum to imply a separate structure in a garden, such as a tent that is built for enjoyment. The glass pavilion is a place of sensory pleasure, where 7,000 years of glass history is seen in and through glass enclosures that flow into each other like liquid. Each individual room in the pavilion is enclosed by a curving wall of low iron, monolithic laminated glass panels 3/4 of an inch thick. Sana's principal, Ryue Nishizawa, writes, "Our concept is to wrap each program element with a curved line drawn like a single stroke of the brush." The program elements include exhibition rooms for glass crafts, multi-purpose room, open air courtyards, storage, and hot glass demonstration shops. In order to keep the main floor free of visual obstructions as much as possible, the mechanical rooms were located in the basement, and the cooling towers and pumps are off-site in a separate building. On the main floor, enclosing all bubble-like rooms, is an exterior envelope of the same glass, but greater thickness of 1 inch. So this outer wall is 1 inch, whereas the interior wall is 3/4. Interior glass rooms float like the exterior envelope's continuous glass skin, separated from each other by a 30-inch air cavity. So this cavity along the perimeter wall, that's the 30-inch air cavity that I'm talking about. And here, it varies in thickness. This zone of air mitigates temperature differences between the outdoor and the conditioned indoor spaces. This is outdoor, this is indoor gallery space. As well as between the galleries and the shops with the glass kiln. So this buffer zone occurs again on the interior, for example, between the hot glass shop and a corridor. It is unlike the air cavity found in a standard double glass facades or the mechanical shafts and spaces concealed in opaque stud walls. This transparent cavity flows like water through the building to make a contiguous air cushion. So usually this plenum, this space for hot or cold air to circulate, circulates through opaque walls like this, or ducts, or a plenum above your ceiling, which is also concealed. Or you can think of it as air cavity in your glass, insulated glass unit or double glass facade. This soft, sensual layering of curved glass and air is a reminder of the former liquid state of molten glass, molded by exhalation of air from human lungs and transformed into a solid. So even though these were machine-made, it's reminiscent of blown glass that could create these curvilinear shapes. Like the Hall of Mirror in Versailles, but with a greater subtlety, the Toledo Pavilion presents a theatricality of seeing oneself seeing, for example, here. Whereas Dan Graham's glass sheets have metallic coating intended to reflect the surrounding environment, Sana decidedly specified uncoated glass. Consequently, the reflections are less obvious. From some angles, the layers of transparent glass appear to create a density of near opaque material. So here, Dan Graham's glass sculptures have metallic coating on them. So it intensifies the reflectivity of the glass and it appears almost opaque here. Whereas at Toledo, there's no coating on the glass. It's as clear as technically possible. And yet you still see layering of reflections through multiple layers of glass. Each of the 360 glass panels measuring 13.5 feet tall and weighing 1,300 to 1,500 pounds were manufactured in Pilkington's factory in Germany. They were then shipped to Shenzhen, China, where they were slumped. Slumping is a process of shaping glass panels over mold at high temperature. So if you take a softened glass and drape over a mold, you can get a curved glass like in the diagram shown here. They were laminated with PVB, that's polyvinyl butyryl plastic interlayer to fabricate the thick monolithic panels. Visible materials and structures other than glass were made inconspicuous. Slender steel columns of 3.5 to 4.25 diameters, that's very slender, and you can see them, these spindly legs, support spans as long as 60 feet and hold up a shallow roof of 2 feet deep. The total thickness of the roof is 2 feet, and you can see how thin these structures are. The bottom of the glass wall, and this is where the bottom of the glass would rest on recessed tracks in concrete floor and are held in place laterally by another track concealed in the ceiling. You can see the track concealed in this white ceiling there. The roof is designed to float over the glass and never bear on the glass panels. So the top of the glass never touches the roof structure, and it's simply resting on the ground. Where two sheets of glass meet, at a vertical joint, like here. They are held with translucent structural silicone. In this way, there are no vertical mullions or channels. Since the glass panels are monolithic and not insulated glass units, the building has no desiccant holding metal spacers that become visible vertical joints in the IGUs, insulated glass units. As a result, the pavilion glass walls appear continuous and ribbon-like. So whereas with these insulated glass units, you would have to have a frame that hold the sheets of glass and the desiccant to wick away moisture. This one has no frame, only the track on the bottom and the top. There are examples of early modern and recent glass buildings that have achieved complex effects with translucent rather than transparent glass. Maison de Verre of 1932 by Pierre Chareau projects the shadowy presence of its occupants onto the translucent glass block facade. So here you see the piano in the background projected onto the facade. In order to provide privacy for the doctor's family and the patients while illuminating the interior, the steel frame facades are filled with glass lenses. These are the glass lenses, infilled with glass lenses that diffuse light with their concave section profile and textured patterns. So these have stippled patterns that cause diffusion of light. In 1995, the Museum of Modern Art organized an exhibit, Light Construction. In the exhibit catalog, curator Terence Riley remarks on the emergence of a new architectural sensibility that investigates the potential of architectural surfaces. Prevalent among the exhibited buildings are translucent, acid-etched glass, perforated metal screens, alabaster that transmit light, and photographic images tattooed on the marble surfaces. The exhibit showed how the use of these thin materials or surface treatments of materials could offer architects new vocabularies. The achieved effects, however, were primarily realized with either translucent or perforated opaque materials, not clear glass. On the cover of this catalog is Sejima, Kazuyo Sejima's, one of her early buildings before she formed Sana. And here's an example of a translucent material, the competition entry by OMA. And a very well-known example of a translucent glass skin is the Kunsthal in Bragans by Peter Zumthor. Another example of translucent skin by Stephen Hall. This channel glass is something he uses often in his projects. In contrast to these diffuse glass projects, the glass pavilion in Toledo is exceptional in its use of crystal clear glass to achieve qualities infrequently found in a transparent material alone. The effect of extraordinary transparency at Sana's glass pavilion is intrinsically related to the problem of heating and cooling, and subsequently the architect's integration of engineering with architecture. Questions of heating and cooling glass building challenged modern architects from the early days of glass buildings. Bruno Taut's Glass Pavilion in Cologne and Paul Scheerbart's book Glass Architecture, both dated 1914, foreshadow the future in glass buildings with double glazed walls, including their capacity to solve glass's critical weakness, which is thermal transfer. Like Taut, Paul Scheerbart believed that technology was, quote, the formative agent of the current culture, unquote, and saw the need to experiment with glass architecture enabled by iron structure. Scheerbart wrote, greater than the diamond is the double-walled glass house. He speculated that interaction between two sheets of glass held a greater potential than a single light, anticipating the transparent poché space between the curved sheets of glass at Toledo. In Shearbart's prophetic 1914 book, Glass Architecture, he contemplated double glass, looking far ahead of his time to speculate what glass architecture could be. Unlike recent glass buildings with chemical coating or other property-altering materials applied to glass, the Toledo Glass Pavilion relies on low iron glass laminated with clear interlayer. This assembly by itself is relatively conventional. The unconventional effects are achieved not with chemical coating or application of other materials, but with spatial organization of crystal clear, bubble-like rooms placed within a glass bubble. The Glass Pavilion took an exceptionally integrative approach to climate control in a nearly all-glass building, a type that is notoriously difficult to cool and heat efficiently. Sana worked with TransSolar, a climate engineering firm founded in Stuttgart, Germany. The pavilion consists of 3 energy zones: the perimeter buffer zone, which is marked in light gray here, the hot glass demonstration area, and the galleries with individual climate control requirements. The hot glass demonstration area is the dark bubble here. And the rest is either corridor or climate controlled gallery spaces. Oh, and the blue are courtyards that are open to fresh air and to the sky. The hot air generated in the hot glass demonstration spaces are recovered and redirected through a hydronic floor slab in order to heat other spaces in the building. So you can see hot glass demonstration here. The heat that's generated by this kiln is redistributed through the floor to heat other spaces like the corridor and the galleries. Cool air collected from the galleries are used to cool the hot glass demonstration zones. So there's circulation of air that happens between cool and hot rooms to balance out the climate. By recirculating heat from the shop furnace, which is kept on 24/7, the museum could have a heat-efficient all-glass building, even in the cold climate of Toledo. Otherwise, the heating costs would have been prohibitively expensive. So this not only serves as a glass demonstration tool, machine, but also as part of the HVAC system for the building. In Sana's design, technical matters are treated as an integral aspect of visual appearance. These include the details of construction process and the placement of columns relative to the glass. The means for heating, cooling, and ventilation are repressed into invisible locations beneath the floor or in a separate building to give the pavilion a simple appearance, despite its highly complex mechanical system. The girders and joints, ductwork, and plumbing pipes reside within the 2-foot depth of the roof, which you can see here. Vertical runs for the pipes and ducts are housed in the full height opaque walls. So there are very few opaque walls, but these would accommodate ducts and larger pipes. The slender columns are mostly solid steel, but some are hollow to run infrastructure and rainwater between the roof and the floor. The Toledo Glass Pavilion is both opaque and transparent, or blurred in its transparency. Kenneth Frampton points out a similar suppression of structural system in Philip Johnson's glass house in 1949. He writes that the glass, the steel frames, and the roof are nearly flush with each other, such that unlike Mises Farnsworth house of 1951 that has a deep overhang here, there is no shadow cast on the building, on the skin of the building at Johnson's glass house. Even though the houses were completed less than 2 years apart, the differences in reflection may be partly attributed to different manufacturing methods for glass specified in these two houses. Johnson's glass house was glazed with 1/4-inch thick plate glass, which would have been shaped by roller, then hand polished. The glass at the Mrs. Farnsworth house was 1/4-inch float glass, made by floating molten glass on top of molten tin and not polished, therefore slightly lower in reflectivity. So the Farnsworth house is much closer in materiality to how we build today, whereas Johnson's glass house was just at the end of the period before mechanization or float glass invention. A more plausible reason for the perceptual difference between the glasses is the play of or lack of shadow cast by the roof. Both the glass house and the Toledo Pavilion, this suppression of structure and the lack of shadow bring the eyes to the effect of transparency. And you can see this almost appears as if there's no glass, except in a few spots where you can see reflections. Frampton calls Johnson's approach scenographic, whereas Mises is always tectonic. The effective Sana's approach at Toledo veers towards the former, although the glass pavilion invites motion like a film, whereas Johnson's house is akin to a still photo. Like Johnson's house, the roof of glass pavilion affords no overhang, and you can see in the section there, absolutely no overhang, thereby eliminating shadows on the glass walls and intensifying the play of reflections on glass. So if there were an overhang, you wouldn't have as much play of reflection there. At the glass pavilion, there is a relatively little hierarchy in the glass specification throughout the building. Both interior and exterior walls are monolithic laminated glass, just 1/4 inch in thickness difference. The gray concrete floor with mineral aggregates is uniform throughout, from the air cavity, the corridors, the galleries, and the exterior courtyards. And this is one of the 2 exterior courtyards that are open to sky. In contrast, there is a clear hierarchy between the served and the service spaces. The served are the galleries, hot glass labs, and the multi-purpose rooms, and the service spaces are between the bubble-shaped rooms and in the basement and the roof. In other words, the mechanical aspects of this pavilion are the most visible spaces that make up the facade of the building, and at the same time, the most concealed spaces buried in the basement and in a remote building offsite. So the glass, the perimeter service space that runs throughout the exterior envelope of this building is a mechanical space, but it is also the most transparent part of the building, and other mechanical spaces are in the most opaque parts of the building. Additionally, Sana took great care to make the glass construction details unobtrusive while amplifying its spatial effects. This was done through treatment of seams, specification of glass, edge finish, and strategic placement of joints relative to the columns. Exposed glass edges in contemporary buildings are often highly polished to make them prismatic, like you can see here, or in the edges of glass steps here. They're made prismatic, then arist. Arist is a term used to describe this 45-degree chamfered angle. At Toledo, the edges at silicone joints were grounded smooth, but left unpolished, like here, to draw the eye not to the material edges, but to the effect on the expansive surfaces. So if this edge had been polished like this, your eyes would go to the shiny edge. And by making that edge dull, they focus your eye on the expansive panel instead. The architects specified low iron glass in order to minimize the green tint of standard glass. So here you can see the difference between green tinted standard glass, which is green, and low iron glass. Furthermore, reflective metal finishes are minimized in the building. The slender steel columns and light fixtures are finished in matte white. You can see the column there. Light fixtures are barely visible. Exposed metals are limited to the stainless steel frames at the glass door here, and the guardrails around exhibited objects, where the shine is reduced with a matte directional brushed finish. So they paid meticulous attention to finishes in order to direct one's eyes to the effects on the glass. The use of thick interior and exterior glass walls result in maximum transparency in a building type, a museum, that normally depends upon opaque walls to exhibit artifacts. The all-glass foyer physically separates yet visually connects the hot lab from the gallery. Without this thermal transparent buffer, these two spaces with highly varied needs for temperature, moisture, and acoustic could not be next to each other unless separated by insulated opaque walls. So normally this room would be too hot to not affect the temperature of this corridor or an adjacent gallery. Normally you would have to stuff this wall with foam insulation in order to have that thermal barrier, but by creating this transparent gap space with glass, they were able to see through the walls into the hot glass rooms. From the glass-wrapped foyer between gallery and hot lab, a visitor can view glass sculptures and vessels against, in the background, the molten glass being shaped into solid objects in the adjacent hot lab. Nishizawa's remark that they enclosed each program with a single brushstroke suggests a space different from one drawn with a pen. Similar to Western watercolor paintings, Japanese calligraphy and brush painting, or sumie, achieves tonality by varying ink density with water. Less ink and more water are used for faint or distant scenes, and the strokes are layered to depict depth. Unlike a pen with uniform line width, a brush stroke varies in width and transparency depending on the pressure placed on the brush and the angle at which the brush glides across the paper. Like a brushstroke, the air cavity that surrounds each bubble-like enclosure in Toledo is contiguous and varied in width. Similar to multiple superimposed watery brushstrokes with a faint hint of ink, transparent glass sheets suggest depth and even opacity when seen through multiple layers. Lighting during both day and night is also handled with great precision and discipline characteristic of Sana's work. At night, when the electric light makes the interior brighter than the exterior, visions of those inside the museum is dominated by the reflections of themselves and the interior objects. To counter this, the surrounding landscape is made artificially brighter to balance the light levels inside and out. So you can see the light fixtures here bouncing light onto the grass ground surface. This neutralizes the extreme differences and makes the glass appear less visible. In the daytime, the light in courtyards provide additional natural illumination for the interior to balance out the exterior light. So here you can see these brightly lit spaces, and the light brightness can be controlled with this translucent curtain here. A high contrast in lighting and constant views of reflections can fatigue the eyes. The quiet, day-lit courtyards offer relief from the effects seen on glass. The natural light from the court is filtered by curtains designed by Petroblaze's studio Inside Outside. The curtain is coated with reflective aluminum flakes on the exterior surface to both minimize solar gain and filter visible light, amplifying the diaphanous qualities of the interior. Observing the glass at the Toledo Glass Pavilion under complex and intensified effects, as well as metaphysical readings of transparency. Observing the glass at the Toledo Glass Pavilion uncover complex and intensified effects, as well as metaphysical readings of transparency. In the pavilion, the execution of a novel plan and material organization is coalesced with skillful lamination and bending of glass in a daring approach to structural and mechanical engineering. It couples technical innovations with Sana's intent to foreground the atmospheric effects over the structure by disrupting the conventional hierarchies between structure and partition and concealment and exposure. From this approach emerges a different kind of intensified transparency of crystal clear glass. In the design process, the architects discovered unanticipated programmatic adjacencies afforded by transparent glass. Bubble-like glass rooms are connected to, yet isolated from, each other by an interstitial airspace typically concealed in an opaque poche. The air cavity appears to fluctuate in opacity and thickness like a stroke of a brush. The effect is soft, fluid, and watery, evoking return of glass to its non-rigid liquid state, cushioned by air. The building is disciplined and precise in its execution, yet dynamic in sensual, intangible effects. In and around the pavilion, the glass continuously presents views of deep spaces beyond, overlaid with reflections of locations far and near through quick and slow motions. Sana's spatial organization of program, materials, and light, combined with blurring of opaque, transparent hierarchy in structural and mechanical systems, result in a complex, intensified space of perception and a novel interpretation of dynamic glass transparency. That is the end of my presentation. Thank you for listening. And I am glad to take your questions.
Yes, thank you, Aki. Thank you so much for sharing your studies and your book. It's fabulous. I have one question first. And of course, attendees, if you have any question for Aki, please just fill your question in the Q&A bottom, or you can also just do that on the chat. So first, my question, Aki, is, as a professional, as an architect practice professionally every single day, is there any kind of the study materials or book you recommend if I would like to know more about the glass material used in my daily practice?
For practical reference, if you are looking for technical references for wall sections, for example, I think the Detail magazine series on glass construction is very helpful. Berghauser's construction manual series, one of which I showed in the slides, I think is also very helpful. And they tend to focus on more highly advanced detailing and material uses of glass. And I think glass innovation is happening maybe more actively in Asia and Europe than in the US. But I think developments are happening quickly so that we can meet the thermal and environmental requirements while being able to create these transparent, open spaces.
Great, thank you. Let's see. Well, if we, okay, here's a question. How far from the glass pavilion is the building containing the wear resistant for heating, cooler, and something like that?
Yeah, I've only seen a plan of it. When I visited there, I wasn't aware at the time that such building existed. It's within a few blocks, I think. It was an existing building. Maybe it was a warehouse. It was an adaptive reuse of an existing building, is what I understand. But within a few blocks.
Okay, great. Thank you. Thank you so much, Aki, for sharing your studies and answer our questions. It's very productive and knowledgeable. And I think there's, okay.
Yeah,
and,
just a comment. Thank you. Yeah.
All right. And well, if there's more question, I think we can end here. The videos and the links. Well, AIA we're going to upload the videos to the YouTube, and we will share the link and share back to the attendees through the email. So please watch our email. And again, thank you, Aki, for sharing your research and study. It's honorable and appreciate to have you be there to share your studies. Thank you.
Thank you for the invitation.
Thank you.
All right.